to the SEG Europe Regional Advisory Committee's webinar series, Geophysics for Today and Tomorrow. Eamon Sedikoff, Chair of the SEG Europe Regional Advisory Committee, and myself, Laurie Weitzel, will serve as your host for today's webinar. Before we begin, the model for the webinar will be a short presentation followed by an extended question and answer session. During the question and answer session, if you'd like to ask questions, please raise your hand in the webinar interface and also put your questions in the Q&A box. Please do not put your questions in the chat box. They might be missed. So our presenter today is Dag Halen Hensen. He has a master's degree in geophysics from the Norwegian University of Science and Technology. And he also has a master's degree in geology from here at Watt University in Scotland. He has throughout his career worked in various technical and managerial roles in exploration and appraisal projects at Norwegian and international oil companies, most notably Chevron and Aker BP. Currently, his role as Global Exploration Advisor at EMGS, he has a partly technical role where he works on how to use CSEM in exploration projects from companies around the world, and also a partly commercial role leading efforts on new business development and international sales and marketing. He has authored or co-authored a number of technical papers, amongst others, on CSEM for conventions, including SEG and EAG, and also at NCS conferences. So without further ado, Dag, please take it away.
Yeah, thank you, Laurie. Starting out, so what I would like to present to you today is what we call kind of a first of a kind of a unique survey. It's a multi-physical survey, including a range of different geophysics, but also some chemistry data. So I'll get back to that. I've been the reason why this survey has come about is because of my business development role, but the reason why I'm here today is because I also do exploration advice. So kind of that is the dual role part of that. Let me see, how do I get down? There we go. What I was planning to go through was what is ATLAB? It's a university consortium. Get a little bit more into the details of what they do and what we have been doing with them over the last year. Then someone's status about the Norway marine mineral industry and how that is shaping up. Then a little bit of learning from previous studies before we sort of entered into this venture. What then the ATLAB technology test was all about, both the operations of that, partly because it's a pretty challenging area. You see the top figure there that it's very, very rough terrain. And then the results from that, which you kind of see on the right-hand side, both seismic, EM, and end up with a, I would say, an initial interpretation, and then summary, conclusions, and questions if there are some. So ATLAB is really a short for the Atlantic Laboratory. It is set up by NTNU, and EMGS have been working with them early stage in the phase called 1. So it's sitting out here, phase 1, and then we had a phase 2, and that was about CCM and MT acquisitions out there. Get a little bit more back to that. ATLAB 3, which we've done this year, is in the same region here, and for ATLAB 3. Now, currently, all these companies are partners in that consortium. So it's a very heavy geophysical attendance there. The previous data was all about the geologic process. So this is the Mid-Atlantic Ridge. And they were trying to understand how that geologic process was by improving on the imaging. And to the right here is a image based on a combined CCM plus MT inversion. And you'll see that you will have imaging all the way down to 120 kilometers, allowing for the geologists to better understand what goes on in the deep subsurface below the ridge here. That is all well and good, but then you sort of come up into the more shallow area. And even then it's still quite deep, but this is mostly using the CCM data, trying to understand the process underneath the surface that leads up to this sort of actually a hydrothermal vent that sits right at my red cursor there. You can also sort of see that from the CCM data, you're starting now to get some structure out of this. And if that combined with surface expression from bathymetry, you see that there's a fault line here, and you can start to understand how these faults are active, where are the basins, and so on. Maybe not at the level with seismic, with clearly the crispness, but at least you're getting the main structures. Zooming in on this section, then you can get the crustal thickness. You're getting now, in this case, conductive values, identifying sediments from underlying more volcanic and other type of rocks, like it's a gabbro sitting out here. And more important, which sort of leads into the mineral basis, is what's happening around this active vent. This is a vent called Lucas Castle. And we know it's venting and spewing out minerals as they are sampled from the seabed here. Quite a bit of copper amongst others, but a lot of different rare earth minerals and various, and there's a number of these sitting in this area. So the question then is really, how can we apply this data to better understand that system? And I'll go down and show you the play. So what we're really looking at here to generate a mineral play is you need some sort of heat source at the bottom, which you typically get then at these ridges. Then you need water to permeate in through porous rocks from the surface that mixes with water that comes up from the fluid source. That is resolving the minerals in the host rocks down here. And they are taken then up through to these vents, and then some of them would be deposited underneath the seabed. Others will come up as smoke and then be raining down minerals, as you see along here. And the minerals sort of dissolve from this solution depending on temperature. So without going into the detail of that, but it's important to understand the complete system from you start with the volcanic here to the depth of the seabed and the water temperature, the host rock. It all plays into understanding what type of minerals you can actually find and the grade of those minerals. So when you start looking then at the EM, it kind of gets a little obvious that there should be some improvement in understanding this play by using the EM data towards depth here. And the initial interpretation that was made for a Nature article published back in 2019 was that these conductive, in this case, red is conductive, will be resistive later in the talk, but here these are conductive, and they're interpreted as being the water percolating down, mixing down here, and then you have the source. You can sort of see that in the sort of conductive layer here that we saw earlier on, that is the heat source upwelling here. You create a heat source and mixing zone here, and then it's stipulated that this is sort of what we're seeing is then the entry point of this warm water coming up to Lucas Castle, and then this more resistive rock sitting on the outside of that. And we can also see there's some resistive rock into the basin. That'd be better on other pictures. But although this data was acquired for more deeper purposes, we kind of saw that, well, maybe this has a say in the minerals business. And at the time that was starting to pick on. So that leads me back to Norway and the Norwegian Petroleum Directorate, who sort of in charge for the mineral industry in Norway. And they have been for quite some time. Here is a timeline back to 2005 up to about now, where they have been collecting data from this area in the North Atlantic, trying to sort of sample and find these sort of hydrothermal vents. So you'll see now that currently along the Moon's Ridge, which sits here, they have found 6 active vents and 3 inactive, and we call them SMS. So deep marine massive sulfide, or there's a number of different abbreviations for that, but I'll be calling them SMSs from here. Most of this work has been done on bathymetry and topography you get from there, from sonar, multi-beam, some video footage. Then they have been sampling this, and they have started to do some geophysical, like magnetics, self-spontaneous potential. And with these data, EM plus MT, most of these are those surface related. And the question is, what can you get out of doing it somewhat deeper? So that is going on, and the Norwegian Petroleum Directorate have said that they'll have a first license round in 23-24. And that is one of the reasons why all these geophysical companies are interested in this area now, as obviously it could be a future market for the companies. However, we need to keep in mind that it's a considerable exploration challenge to find commercial deposits of minerals, which you can also excavate. We are, at least in Norway, assuming that active vents, which has a unique ecosystem, will not be excavated for mining, but we need to find extinct event, and that is pretty challenging. These deposits, they tend to be in the hundreds of meters, so maybe up to a kilometer long and a few hundred meters. So it's kind of finding the needle in the haystack, or as I said here, a football pitch in the North Atlantic. So far we found 6, but it's relatively easy to find active ones because they will have a geochemistry signature in the water column. So you can kind of use that to define where they are. The challenging one is those which are buried, and they might actually be the largest ones. And finally, out of I mean, you see these dots here, these are discovered SMSs around the world. There are other areas where these are licensed in red marks. But out of these 200 sites, it's estimated that only 10 of these would have sufficient size and grade to be considered for mining. So keep in mind, it's not just about finding an SMS with minerals, it's about finding something with high enough grade and being large enough to actually do something commercial. And it's not inexpensive to start operating in the middle of North Atlantic. NPD has very recently come up with a resource assessment for this part of the world, if you like, but that is not scope for this talk, so I'll just leave that for now. But just for your awareness, there are some estimates for that. Going into the Atlab area, we have been studying now the area between the Lokeslottet, or Loki's Castle, and Månskatten, which is called Mån's Treasure. So I'll be showing you data from this area where we've been collecting data. This is a SMS in an axial position sitting on the actual ridge itself. And then the other typical play is when it sits in a flank position like this, like the Mån's Treasure. So there's an active hydrothermal field here. This one is inactive, partly buried. The flank positions are considered to be to have a higher potential because they can sit there for a longer period of time and accumulate in size. And then also in this case, they are sheltered from sedimentation that comes from the northeast. So there's a lot of things to think about, but we're sampling both of these in order to understand how to best find them with geophysics. This is a model from Mån's Treasure showing you the sizes. So it's about 500 meters long, and the elevation is about 270 meters. So, and they're all down at 2008 to 3000 meters. So it's not trivial to just go about and find them. Up until now, as I said earlier, most of that has been done with bathymetry. But the aim and the motivation for Atla was to get now going from geologic processes, which Atla have been doing, to actually how can we use CCM and seismic plus other techniques in mineral exploration. We wanted to create a cost-effective solution that could map these deposits below 2,500 meters subsea, which in itself is a little challenging. Preferably identify mineral content. That would be ideal. That's a little bit down the road, I think. The current exploration methods are primarily surface expressions, water column chemistry, but also some shallow remote sensing technologies have been used, but they are fairly shallow, those methods. Then the question, how do we map these deposits best, particularly the ones which are inactive and particularly ones if they are buried slightly with sediments and or volcanic flows. That might be a little bit more challenging from a development point of view, but clearly some could be covered by a few meters of sediments and you would like to pick them up. And we would like to map these subsurface towards depth with independent geophysical data sets and preferably being able to discriminate in this case, basalts from massive sulfides. When you're looking at electrical resistivity, massive sulfides are very conductive, and its typical host rock basalts is very resistive. So and both of them would have a high acoustic impedance, so they would be ringing, if you like, on the seismic high amplitudes there, but it should be discriminated by the CSEM. And that was the goal, and we'll show you later how that works. We did look a little bit into what has been done before. There is one particular area in TAG which has been studied quite a bit. So that's a mid-Atlantic ridge further south. And this is a paper by University of Southampton and GeoMar on using a towed receiver across this area. And I'll show you the results in a minute. I just also wanted to note that similar methods has also been used by the Japanese outside of Japan, where they were using a electric tomography and a towed receiver system like that. They were able to map out actually minerals at various depths. So it has been tried before. The question is, how can we improve on that? Going back to the one in TAG, if you're looking at the next page here, you'll see that the same map and the sites where they have minerals, they can show up on magnetic anomalies. They tend to blur out a little bit here in pinkish. But with the conductive, you'll see that they are more narrow and more associated with the actual deposits themselves. So it does clearly look that using EM and the conductivity or resistivity, if you like, would be a good way. And this is the cross section showing that the conductivity increases, and you can probably also map out the thickness of those minerals. So that is promising. The question is, can we improve on that, and can we make it cost effective, and can we add other data on top of that in the same go? So that's what AtLab wanted to do then. We wanted to acquire a range of seismic data, so bottom profilers, P-cable seismic, streamer 2D, OBN, and then seismological tomography data. And out of these 5, it's really only P-cable that we were not able to do this year. We ended up on just doing streamer data. On the EM side, we wanted high frequency EM, including IP and UAV, towed EM, CCM data, and MT. And we were able to get 2, 3, and 4, and some high frequency, but we haven't really gotten to the IP and UAV type of it yet. But we have a range of EM data. So we set up a cruise. We had 10 days. This was in the boxes here. It sort of said what we wanted to do. And we were going out there for 10 days and doing as much as possible. Seismic, environmental data, and EM data. And there were 3 aims of this cruise. One was to rig 1 sole vessel, so that has to do with mob demob cost to keep that low. And it has all to do about being cost effective. Then we wanted to better understand which of these various geophysical techniques is good to use in the subsurface characterization, meaning that we wanted to acquire these data over known accumulations, such as the Lucas Castle, the Moon's Treasure, and also MPD had a prospect sitting right there, which they wanted to investigate, and that's why we had this little mini 3D. This 3D is also then very useful to understand how does the 3D effects compare with the 2D, because there is clearly some issues with topography that can cause imaging artifacts here. And finally, together with the EM survey and simultaneously acquire a range of chemistry data, such that we will understand whether there are ecosystem along in the profiles that we should be aware of. And particularly this has to do with obviously mining. You don't really want to find a prospect that has a unique ecosystem. So can we early on map and see how that varies, and if there are ecosystems everywhere, or if they're just sort of isolated to the actual active vents. All of this then would have to be done in an area that is almost like going into the Alps. So this is a picture from the AtLab 1 where we acquired the data, and we knew we were able to do that. The question is how close you can get to the seabed. In order to do that, we rigged a vessel. So this is what it looked like. We, starting at the bottom, we placed nodes. So this is the EMGES nodes that we use for the oil industry. But in this case, we also added some seismic nodes that we dropped alongside with the EM nodes to give us the wide azimuth seismic. Then we have our conventional source with our conventional system. But we did also come up with some towed EM receivers that we can tow in addition, similar to the University of Southampton did down at the tag. Finally, we had PGS providing a geostreamer cable and a gun. And we have echo sounder here, and we have echo sounder on the source down here. This is a multi-beam from Norbit, plus the chemistry data was attached to the source right there. So that was the system we went out with, and then we had 10 days. I'll show a little bit of cartoon of how this works. So first we drop the nodes as we get out there. So we have this vessel containing the nodes. We survey the bottom so we know where we are placing these nodes, because you can see that it's quite important. Then we drop the nodes free falling down to the seabed, move the vessel, and survey it again and drop another node. And that's how it is. So then we have nodes sitting along here, including 2 seismic nodes. In this case, there's actually 5 altogether, but just showing 2 here that were delivered in April that were dropped. All of these nodes will now be sitting on the seafloor until we final the survey so that we can get as much empty listening time as possible. Then we do a seismic survey across here. So PGS tows that along. It's no big sort of secret on how that happens. That's fairly trivial, just sort of taking care of the wave height on top. We were using a 1200 meter dual component geostreamer with a 90 cubic inch single gun. So a little weak gun, but the data proved to be better than maybe expected. And then the seismic nodes. And this is a first peek on what the data looks like. Then we came back and we acquired EM. We have now the EM node sitting down there. The challenge acquiring EM is that you need to get as close as possible to the seabed. And you'll see this cartoonish here, that it's not necessarily the easiest. Now things are not to scale here, but just as an illustration. But that's how we went about and did that. And while we acquired that, we also, over this little 3D, I'll show that in a moment, acquired a towed receiver system. So we didn't do the towed receiver system everywhere because of operational challenges. But we did the multi-beam and we did the environmental stuff plus acoustic well monitoring along as we went and did that. So over the 10 days, this is what we acquired. We had this data sitting here from before, so that was not acquired now, but we did acquire this regional line with CCM and MT. And then we acquired a mini grid with a towed receiver and CCM sitting up here over this prospect that NPD had. And then we did seismic. So we went along here and did essentially all these lines, including these turns. So we could calibrate the EM and the seismic at the same locations with a mineral deposit sitting here and a mineral deposit sitting up here, up here, and then over this prospect. One of the challenges then, if we're going to EM and this topographic high, is the ability to get close to seabed. And we need to be fairly close in order for the EM signal to transpond and not get diluted. I'll show you the results from that. So if this is the flight, and this is the seabed, so you'll see that in areas we're up to 800 meters above the seabed. And the question is, are we getting data then or not? And that's what we were not quite sure about that. Looking at the low frequencies and judging from the magnitude of that signal, you'll see that the magnitude varies as we go down here relative to the height above the seabed. So yes, it is clearly an effect, and that we were aware of. But for the low frequencies, we are getting good signal to noise and good data. Looking into the higher frequencies, 3.5 is still quite good. But we are getting some noise problems at the bottom here. But as we go into the 17 hertz, you'll see that the magnitude, like in this one here, they drop quite more considerable. So we're losing some signal on the higher frequencies. Then the question is sort of how does that impact the data down the line? And when we invert that, we actually compensate for that flight height. So the inversion process, it's a 3D Gauss-Newton inversion, will be able to sort of compensate for that, and hence we don't really see this variation of flight height in the inversion results. However, we do expect that we will have lower resolution in very smaller details, and I think we see that of this moon stretcher here, that we will be struggling to see the mineral content. We're seeing some, but not as pronounced as we see in other places. But the quality of the data is good. And the reason for that is that we knew we were in rough terrain. We'd been there before, so we picked the receiver positions a little bit better than previously, making sure that they were staying in flat terrains. Last time we had someone tumbling down the slope and everything. We have a 1200 ampere source, so that's significantly stronger, I believe, than other ventures similar to this have been used before. And but we did have up to 800 meter flight height at times. But because of the general resistive environment we were measuring this in, and the large difference between minerals which are conductive and basalts, we're getting quite good contrast. So essentially, the imaging has worked out, I would say, probably better than we were expecting. But what we also saw was that we could have a larger pitch angle on our source, allowing us next time to go possibly even closer to seabed, because we could go up steeper than we could in this case here. Or we would have to sort of plan the path slightly different. But at higher angle frequency, it might be an effect that we're not able to see everything we wish we should see. So I just sort of taken out the figure here, and then I've sort of zoomed into this little cartoon, and so this is your resistivity and then the conductivity. I'll come back to the difference on that later. But here I wanted to compare that with seismic and showing how sort of seismic and EM compare, they compare and contrast, but they are pretty complementary, seeing a resistive sort of feature into the basin here, and then you're getting, as you go deeper, you get more and more resistivity down here. Sorry, this was conductive, of course. Then let's go to the seismic quality. This is a line across, this is moon stretcher right here. And it's obviously challenging terrain. We are getting quite good image at the very top here. We are seeing we're clearly seeing the large fault, but we're struggling as we get deeper into this. Here we're seeing a basin, we're getting quite a lot of reflectivity. It's a pretty complex geology, so it's not trivial to sort of map it out directly. But I'll show you some sort of zoom in onto this. And if you're looking into the shallow area, which is really the target for this, we are seeing that you see the sediments, which are sort of nicely coming here, while the volcanics, or like the volcanics, possibly stipulated to be minerals, have a very different expression. And also they will be pinging us the amplitude contrast between the shallow sediments and these. So we can argue that when you're looking at moon stretcher, this mineral deposit, that you can characterize the substructure of that in the shallow part. So seismic gives the ability to map out geometric forms and understand this deposit a little bit better. And then you'll see the sedimentary basin really well in between, but the deeper part of this has quite a clear challenge. So concluding on that was that we actually thought that the imaging was better than expected through the complex basalt and into the sedimentary basin, even given the small source we were using. Maybe in the we would have liked it to image a little bit deeper. We're seeing down to about 1,000 meters. That was somewhat less than expected. It might be PSTM could improve on that. A bigger source probably could improve on that as well. However, the moon stretcher is really well imaged down to about 30 meters. And in areas, we can also see some faults, possibly mineralized. I'll show you a little bit of that later. However, when you go to this Lucas Castle, which has a really rugged terrain, we're seeing a lot of side sweeps, which is challenging. And that is probably a 3D problem. So we solve it this time by using a high density multi-beam bathymetric map to sort of cut them out. But they are causing some problems. So 3D seismic is clearly preferred because it's really a 3D problem imaging these things. Then going to the CCM and calibrating 3D or CCM versus the 2D we had. So this is the line across the Lucas Castle, the old line we had, and then we want to compare that with the mini 3D we have here, and then the seismic line coming up here. So this line we're looking at is the one in red, and it's a large fault. It's a large horst sitting up here with some large deep-seated fault sitting down here. And then there's a basin in here, and then there is a highly reflective seismic body sitting here and one deeper down. That doesn't really match up with the resistive feature on CCM. So the question then is this because of minerals and that the resistivity is further down, or are we having some imaging problem with either of the surveys? And when you start looking then at the 3D, which gives for more data, you can see now that the resistivity of the 3D CCM lines up with the seismic body, and essentially indicates that this is all volcanic or basalts. And this is really a result because when you have a 3D, you get better depth placing and you're getting the stability of the inversion improves significantly. But it also shows how seismic is able to calibrate the CCM response. And then going back then to the looking at the 3D CCM with the 2D CCM, we see that in general, the 3D, the CCM matches, it's just that it gets out in depth, so it should have been placed higher up here, or possibly these two slightly further down. But yeah, it is a 3D problem out here. So although we're getting in general the large features, the depth placing is something that we need to be aware of. At the shallow though, it does appear to work really well. So it's really more of a question of the deeper things going down there. But that sort of is interesting because then you get to the interpretation game, and this is what the combined seismic and CCM looks like. And yeah, it's a fun area to be an interpreter on, and you do want to start to wonder what's real and what's not. But these things are related to big geologic structure we understand. So this is the Mid-Atlantic Ridge again. The question is really what's happening here and what's happening here, and that's what we need to sort of have a closer look at. Also, sort of whether you're having conductive zones combined with the EM, could that possibly be minerals relative to seismic events where you have high resistivity? But before we go to that, we need to sort of understand how to work with the EM data, because EM data working in this setting is very different from working with EM in oil and gas. And the reason is because we are in a resistive environment looking for conductors, and we are in an environment that varies significantly in dip. So we've done a quick sort of modeling study just to facilitate that, putting in or using our background model, which you see in the back here of the resistivity, and then we added in a conductive vertical layer, a horizontal conductive layer, and the same for resistivity. And then we forward model them and invert them back and see how do we best image them. Then essentially 4 products you can use: horizontal conductivity, vertical conductivity, or resistivity. Obviously, these are the inverse of each other, but it is more about sort of where they are a better image, because of the color scale is always a challenge to sort of be able to highlight the levels. So what we do see is that these conductors, the horizontal conductor is well imaged here on the horizontal conductivity, but to look at the vertical, you need to you need to go to this vertical element here, but probably better vertical resistivity that really highlights that. It can, to a certain extent, also be seen in the horizontal resistivity. And looking then at these guys, this is typically coming out in the vertical resistivity, but then also the vertical one needs to be in the horizontal one. So you kind of have to jungle this around a little bit, and I'll show you some modeling that shows why it's not trivial, but you kind of have to look at all these sort of volumes going forward. Because what we did as well was then to sort of, okay, so we understand, and now it's not trivial. What does these prospects and the bodies we're looking at, what would they look like on the EM? So we made a model where you had a conductor at the dip here, because we actually have some possible leads sitting there. And then we have a resistor that would be a volcanic event. So this is a mineral event, that's volcanic basalt event. How would they look at these different products now? And this is the vertical resistivity. Again, the resistor comes out really well, but the conductor comes out, but there is slightly some imaging challenges, and there's a couple of few more imaging challenges comes out. Typically is imprints, so that's something we need to be aware of. Underneath the receiver that sits there, we will have some imaging challenge with imprints, and the same over here. So that's something to be aware of. But you will see that they vary a little bit between different products. Horizontal resistivity gives us a pretty nice outline of the conductor, but we do have some challenge at the top. This is typically a TTI problem, but in 2D, we're not able to run TTI inversion like we did do on the 3D. So that's another reason to go to 3D. And then you can go to the conductivity that highlights this bed. So you kind of, it's just really an imaging, a visualization of that. While there you would then lose the resistor. So that sort of adds up, sort of, these are probably the two most, the best products for mapping these types of prospects. But the conclusion is that it's not always very clear. So we tend to look at all four, just sort of see how they respond every time you see something, and then being aware of the physics, because horizontal vertical resistor will typically be best in vertical resistivity of the picture. So you need to sort of look at that and then compare that to avoid falling into imprint traps and things like that. But we have also seen, and I'll show you forward, that combining now Seismic and CSEM is very useful, because you're then getting complementary techniques that could show which of these bodies are valuable and which are less. So that takes us to the interpretation. Starting, I'll show you this line here. This was the first line we acquired from CSEM, but where we have now also the 3D EM data sitting in this area and the seismic data sitting underneath there. But it all starts with the surface expression and all of these faults, because the elevation is so big. We're talking 1,000 meters of throw here. It's pretty obvious what it looks like, but we don't really know how the faults are moving underneath, but we can estimate them. We do also know that we have Locust Castle here that sits in this rift valley, but it sits on a ridge that's uplifted, and it's really active. You can also see a volcanic center sitting along here, and you can see volcanoes all along in the area. So you can get a lot of good sense just by looking at the surface expression, and that's what's been doing before. But we want to sort of map what we see out here, the heat source, what's going on in the middle, and compare that with the, which I mentioned earlier, Monstresher, and then the Locust Castle, which is here. This is then again what the seismic would look like. We know that we have some uplifted older rocks. It's sampled here. It's a gabbro. We can see now the basins, and there's an uplifted rock, but it's not much of signature in the seismic in these older rocks, and it's not too much underneath the Locust Castle here in the active spreading ridge either. But we can put on some interpretations. You're getting some better faulting, some better stratigraphy, and you have some side sweep effects. Focusing in on that, then you can start sort of in the basins at least to sort of differentiate the different fascias. So this is sort of an active volcanism that has been buried by sediments with some recent volcanics going into that. So just sort of understanding that brings on at least so you get the picture and geologic history of the area, because that happens here. But on the other side here, the volcanics are active now. So then you'll have this layer at a very early stage. So it's important to, from understanding where is the play, where are likely minerals to be. Yeah, so that was this one over here. But then I said, as going to the Lucas Castle here, it's quite challenging to get any information on what's going on underneath, other than that it's a high, there's some faults, but it kind of stops there. So the question then is, how can EM bring some insights into that? So this is the same line then with a horizontal conductivity. And we're seeing some sort of very clear blue areas. I'll be focusing on this. There's a apparent conductive body sitting right there. This is a receiver imprint, be aware of that. And there's some clear conductive bodies sitting down here as well. And these are the ones that have been associated to the being a part of the flow Lucas calls in an earlier stage. If we now focus in on that conductive body, so that's sitting right here. There are some receivers there. We're making sure that we're not looking at imprints, but it's a clear body there. When you're looking at that same area on seismic, it's actually sitting right here. So there's also there on seismic something sitting this area. This could possibly be sediments which are downfaulted, and these are sediments hanging up. But there's also some very distinct bright events along this fault. So something there, if you map that out, you can get a body similar to that. And when you compare that back to the geology, no, to the EM, you actually have a conductive body that fits with a seismic body that could be have some sort of meaning, and it certainly has a mineral response to it. And if we now take the learnings from Lucas Castle, from this Nature paper, where it's claimed that we can see the convection cell of the water percolating in, being heated here, and then coming back up. One can argue that there's potentially something similar going on here, and that this this fault plane here is an active source of warm water and a volcanic system, potentially spewing and mineralizing this area. And it's well worth noted that this area sits on trend with the Mondstrecke further to the south. So it's in this sort of flankial position towards this older rock right there. So that's what a combined geophysical picture would look like. And you can take that and sort of start to interpret out a little bit more what you're seeing of the geology. So having this starting with the moho at the base, having possibly convection cells here and here. As you come shallow, it's easier. This is a volcanics and a primarily basalt layer, but then it's primarily sediments with some recent basalt sitting on top here, with a potential mineral response sitting along this flank. This model for that is, if we go into the Mondstrecke, that's what the NPD claims that looks like. So something coming from the subsurface and then mineralizing and spewing out and being active on the flank side here. So possibly that could be what we're seeing there, but that needs to obviously be sampled before we agree on that. Then final interpretation here, it's more of a testing a prospect. As I said earlier, MPD had a prospect sitting underneath here, so that's why we made this little 3D, 800 meter spacing between receivers. There are some very strong seismic amplitudes related to this area. And the question is, can we differentiate them and possibly find a mineral lead on this one? The answer to that, I guess, is no. These strong seismic events are all resistive. They might be a little bit weak on the one top, but if you adjust the color bar, they will come out as very resistive features. And this is a basalt sitting underneath. So that is sort of how you can use the combined integrated approach to differentiate what seismic amplitudes would be. Are they either minerals or are they the volcanic basalts, which typically are? So that sort of concludes the talk. Come back to the summary. We have acquired now a multiphysical data set in the area. Currently, only the 2D seismic and the nodal CSEM is processed, but The understanding of that is that it allows for better interpretation and an understanding of the complete subsurface. The data looks to be very complementary. I think we can improve the seismic with EM and improve the EM with seismic. And also there are some observations of possible leads and possibly condemning previous estimated leads. The towed EM, nodal seismic, high-res multi-beam and environmental data, they're not ready yet, so we'll have to come back and talk about those later. We do know that there was some water depth issue though on the water sampler. It failed because of pressure, and only one out of the nodal seismic were in the end active because they happened to be adjusted wrongly and turned off when the temperature was below 0 degrees, which they were. So we only unfortunately have data from one nodal seismic, but that yet to be processed. So if we conclude on that, we have seen that the seismic data image says well the upper shallow, and essentially this part, the interesting section with respect to minerals, albeit there are issues with side sweeps. So 3D data is clearly preferred. And 3D seismic, you can fairly cost effectively acquire that over large areas, and that could give you a good data to screen for possible mineral sites. What we have also seen then that the EM data, it's pretty good imaging both at shallow and deeper levels. The shallow detailed imaging can be challenged in places because the towing is so high above the seafloor, but we should be able to come further down next time because we can increase the pitch angle and tow out quicker. We also see that the EM nodal data has a significant better resolution and imaging towards depth than what we have seen observed in the literature. And also from the first sort of initial run from towed EM, I didn't show that here, but the nodal data is clearly preferred in that sense. And what we have also seen in further survey analysis is that it's actually, you don't really save much time on acquiring the towed EM instead of nodal data because you need to tow closer. So you can get away with denser or more sparse nodal data, and the timing is the same. So I think going forward, nodal data will be there, but let's double check that when we get the towed EM in. The combined approach of both is that when you do acquire this simultaneous in the same area, we get an uplift on both data sets, and understanding of the geology improves significantly. So that concludes. So then we can take questions.
Thank you, Doug. Thank you for a very interesting topic and both very well description of the methods of acquisition and integration and integrated interpretation of the method of the results. We have a question in the question box. I can read that. Yep. So, hey, Doug, regarding the seismic source being used, what was it the same as an AMGS sources used in oil and gas? Thanks. Guess maybe in this regards, just generally the sources could describe.
Yeah, in the EM source we used not our latest and greatest. We used our conventional source, which has 1200 amperes. So we have a more modern one with up to 10,000 amperes, but we did not use that for this one.
Okay, thank you. I have another question. You use the seismic data as well in your analysis. What about the inverted seismic data sets for high frequency velocity inversions or other property inversions in the very shallow with the use of the node data? Have you looked into that?
No, that hasn't been looked into yet. The data I've been using now is what TGS has been processed, and then Shearwater has done the same. But we haven't gotten to going beyond sort of time processing yet. But I clearly think there is potential. I have partly studied the velocities of the seismic, and I can see there is a correlation between seismic velocities and deeper EM response as well. So I think there's some uplift to be had there as well.
And one other question I had as well is, how do you see, you described a little bit, but maybe you can elaborate, how do you see this exploration type will evolve in the future with the learnings that you have? And also, if you take into regards the activities that being done towards, let's say, very shallow investigations for placing of the windmills, They're also investigating shallow overburden. So how would you describe in the future of this type of explorations, future activities, future methods of exploration?
Well, if we start with the marine mineral side of it, because of the depth of this, most of the surveys so far are being done with the AUV, and that is it's pretty darn expensive, and it's pretty slow. I think there is a potential here to do this with a 3D seismic first to get the understanding where you want to go, and then do targeted EM following. Our data really indicates that the nodal data is the way to go, both from a time point of view and from a quality point of view. So I think it would be more of large 3Ds with smaller EM surveys. And then when you make a discovery, you might want to go down with a AUV that can hover and measure CCM, because the challenge here is really that these deposits, particularly this part of the Atlantic, when you go further south, they tend to be a little flatter. So it's easier to acquire data, but the challenge here for both AUVs, typically the Hugin type, and our toad system, is these large mountains that you run into. So you need to tow out, and you don't get as close to getting the resolution you want. But there are solutions where you have AUVs that can hover and can bring the same system, but that is obviously time consuming, but that could map out the detail. So I think you'd have an exploration phase where this type of method use, and then you have a different thinking for appraisal and development. On the offshore wind, I think well, part of the reasons for why we and these other companies were doing this, because we wanted to understand how to simultaneously acquire this data. I think offshore wind will see more and more of the P cable system, or P cable is the PGS owned now, but there are Sercel and Magseis have developed similar systems to that, which have very high resolution and gives you a small little 3D effect. And if you add EM together with that, I think you will then both see the stratigraphy, but you can also then get the parameters of the shale, which is important when you sort of try to dig, or not dig, but you bank, or how you say that the large sort of foundations for the monopiles. And when you put them into the surface, you can't sort of take them out again, or you can't change position. So it's important to do it early on. So I think it's a potential large market going forward, and important market, and also again, combining EM methods with seismic gives you more independent measures, and it gives you more rock properties that makes geotechnical design better and easier.
Thank you.
Thanks, Dave. That was a wonderful presentation, a good example of integration. I have a couple more questions, if I can, that have come up. I appreciate the point you were making between the logistical efficiency of towed system versus an AUV. But I'm not sure if it came up during your presentation, but it seemed like you were acquiring with the towed system across the bathymetry. Would it have made sense, or would it have been possible to acquire those tow lines parallel to those ridges and get closer to the seabed?
Yeah, it's something we considered. Actually, the Mini 3D was acquired parallel, while the 2D lines were acquired across. The challenge about if you were to acquire 2D along the ridges, you will get so much side sweep effects and all sorts of anisotropy issues. So that's why we had to sort of be more or less 90 degrees on the main ridge trend. So that is a challenge, but and we did sort of look initially at having a survey going close to the Moon's treasure alongside, but we essentially run out of time, because it takes quite a bit of time to sort of position yourself. So we said, let's make it simple. Let's do this 3D in an area where it's flat, just sort of to make sure we start easy, and then we can build on that when we learn. But the challenge would have to be to get down onto these the actual areas where the minerals are.
Yeah, and I appreciate your comment earlier that you saw that you could perhaps go with higher tilt on your transmitted dipole. because of course, I guess you have navigational information on the head and the tail, so you can incorporate that into the inversion, go to higher dip and maybe get closer to those strong slopes.
Yeah, at least from a data quality point of view, we can do that. So the question is on operation side, how much we dare to do, but at least we should be able to tow out and pull everything up quicker and still get data which has high quality.
Yeah, that would be an improvement. You also mentioned anisotropy problems. In your integration section, when you were comparing the vertical and horizontal resistivity and conductivity with the seismic data, did you try, or would it have made sense to have a look at the ratio of those horizontal and vertical components to aid your interpretation?
Yeah, I think it would. I think we just need a little bit more time to understand both the EM, but also sort of how it compares with seismic. So it's a little bit early stage for being quantitatively in feedback on that. But I think there's a lot of learnings to be had, and I think we're just scratching the surface at this point in time. But
yeah, I appreciate that. It's early days, and there's probably a lot more you're going to get out of that pretty rich data set.
Yeah, I don't think it's early days, as I say, but it also sets up the examples of future service of the same sort.
Very true, yeah.
On how to run exploration, what sort of measurements, what sort of service we should run. And it's always like what also mentioned for offshore wind exploration projects, where they set up the files at the places where to put out the installations. Once they put it, then it's there. So then you need to do quite a lot of analysis up front. And as you say, it's very kind of important to have an integrated solution that we perhaps we can combine different measurements and get the best out of the two solutions. Are there any particular reasons why P-cable was not implemented in your approach? Was it more just separation reasons, or was it something else?
It was an availability reason. So it was just not available for the time, and we had another cable that was available. So sometimes it's just sort of those simple reasons, yeah.
Yeah, but then you have quite a substantial program, so that's quite cool to see what you presented.
Yeah, we did get to do quite a bit more than we actually thought so early on, because when you plan, you need to be conservative and everything takes time, but things worked out much quicker than we expected, so that was good.
Yeah, you prepared better for the next one as well.
Yeah,
right?
exactly.
So
we know a little bit better, yeah.
Any other questions from the audience? Then we thank Doug for a great presentation. Thank you for all attendees.
And thank you for allowing us to present the data. So first go will be more of this.
Excellent. Well, thank you, Dag. Thank you, Laurie, and thank you, Emin.